In this problem, we have a series of train cars colliding on tracks, which present us with a classic conservation of momentum problem. Let's start with drawing a picture. We've got one railroad car moving with some velocity, and it collides with two more cars that are already connected together that are also moving in the same direction. Right, so we get this collision here, and they give you a mass. I'm just going to put M here as the mass of that car. And it turns out these other two also each have a mass M. Now, they tell you that the mass of a single car, M, is 1.8 times 10 to the 4 kilograms. 1.8 times 10 to the 4 kilograms. It's got it in scientific notation. That would be 18,000 kilograms. If you prefer to write it that way, you can, but I'm going to keep it as it is. We know that this one is going 3.4 meters per second, and these combined cars are only going 1.2 meters per second. Everything appears to be moving to the right. It's good convention to indicate which way we're going to call the positive direction. And what we have here ultimately is a collision where they stick together. It's a perfectly inelastic collision. So I'm going to draw my dot, my therefore, my after the collision. I've got limited space on the right side with this long train. But I'm going to put all three together. They're stuck together, and they're going to have a new final velocity. All right, and this is all three M's. So when I set it up this way, if you look at momentum, these are clearly cars pushing on each other. But if we look at them as a system of three different cart masses, then there is no external force on the system. We can assume the collision happens and the time before and time after is really small, and therefore we can ignore the friction, any air resistance. And so we can say the momentum of the system before, P system before, is equal to the momentum of the system after. So that's what conservation of momentum is. And I'm going to, just for sake of simplicity, I'm going to call that train part 1 and train part 2. And so what the system before would entail would be the momentum of the first cart at the beginning, plus the momentum of the second at the beginning. And later, the first cart will have some final momentum, as will the second. And if we say that P equals mv, I can break it down even further. The mass of the first and the velocity of the first at the beginning, I for initial, plus the mass of the second set of cars, the velocity of the second at the beginning, is equal to mass of the first, the velocity of the first at the end, and the mass of the second and the velocity of the second at the end. And in this particular case, we have a collision where they all stick together. It's a special kind. And since they've stuck together, they're all moving at the same velocity. Right? So you end up having this combination of masses where they stick together and become one combined mass moving at a final velocity, right? So we get this equation that simplifies. And so let's move in here and start to plug in some things that we know. I already wrote down the mass over here. Let's label this. This is going to be the mass of the first cart. And we can write the mass of the second cart, which is really twice the mass of the first. And so I can say that it would be 3.6 times 10 to the 4 kilograms. We know the velocity initial for each. The velocity initial for the first is 3.4 meters per second. I'm going to put a plus because it's a velocity. Even though everything's to the right, and I anticipate everything to the right, it's always good convention to have the plus sign. The velocity of the second one at the beginning is to the right, also at 1.2 meters per second. So I've just listed all my variables, and now I can plug things in. So over here, I'm going to write in 1.8 times 10 to the 4 times its velocity of 3.4. The momentum of the second one is 3.6, twice the first one, right? Times 10 to the 4, and its velocity. And so that would be the momentum of our system if we add them together. And so on the right side, if we add 1.8 and 3.6, I get 5.4 times 10 to the 4 kilograms, moving at some final velocity. So I just did a little bit of math. I plugged in. Hopefully you can follow along with what we got here. Let's pull out the calculator, find out what that total momentum is. When you use scientific notation, I like using the EE feature, 1.8 second common, puts that EE to the 4. That should be 18,000. Indeed it is. It's a nice shorthand convention. I'm going to multiply that times 3.4. So that's the momentum of the first cart, 61,200. 61,200 plus, let's do the momentum of the second one. That would be 3.6 second e to the 4 times 1.2. That's the velocity of the second set, 43,200. And that is equal to 5.4 times 10 to the 4 times that final velocity. And we add those two momentums together. Let's add 61,200 for a total momentum of 104,400. And lastly, I'm going to take that value and divide it by 5.4 second e to the 4, which is the total mass, and I get a velocity of 1.93. The final is a positive value, which I expect, 1.93 meters per second. All right, so if I compare that now, if I look back, it's always good to see if it passes the smell test. I've got a fast cart and a slower cart. They hit, they collide. It looks like that first car is going to slow down when it picks up those other two masses. And the double mass vehicle is actually going to be going a little faster. It was 1.2. It got bumped from behind. It's now going 1.9. And the fast one is going a little bit slower. So you think of like a rear-end collision between a small car and a big truck. That big truck would speed up a little bit, and the small car would certainly slow down. So that answer makes sense. That's always an important thing to check when you work through a problem. So our answer here, I had 1.93 meters per second as the velocity of the entire set of 3 carts.